Good morning, everyone. Since it's our new unit, let us go to our table of contents page and put where we ended our last unit 3 and label the next one as unit 4 derivatives with the new page number that you're starting with. After you've done that, let's take a look at your warm-up here. Again, we're going to be talking about average rate of change, which is dealing with derivatives also. So we are going to be doing the average rate of change for g of x, which is square root of x, and also the average rate of change for f of x equaling x squared. So just as a quick refresher before you start doing that, average rate of change, let's look at this one for a here, 3.5 comma 4 for g of x. So I'm going to find the average rate of change for that. So I'm going to do the square root of 4 minus the square root of 3.5 divided by 4 minus 3.5. If you do that in the calculator, you get 0.258. All right, keep going, pause the video, do the left side, BCD, and also for x squared, ABCD. The next slide has all the answers. Okay, so here are the answers for my g of x function on the left, my f of x function on the right. Hopefully you all got the same answers there. Check your answers there. What we're going to take now with these is we're going to rewrite each of these 4 average rate of change problems as limits. So how would I write these as limits? So taking a look at what g of x was, which was square root of x, I am taking the square root of x minus 2 here, all divided by x minus 4 as x goes to 4. How do I know this? Well, the instructions for the warm-up there, the average rate of change, we had to figure it out from 3.5 to 4, from 3.9 to 4. They were both dealing with 4s at the end, so that means my limit is going towards 4 there. And then we know the pattern that if we plug in that limit value in there under the root, we get the 2, so that's why there's a 2 here. And all these answers, if you notice, are getting to be close to a fourth, 0.25. For the next one here, also for root x, here I was asking you to go from 24.5 to 25, 24.9 to 25. So that is the limits going towards 25. And again, it's root x. How do I get the minus 5? Because you're plugging in that limit value there to get the 5. And the bottom is x minus 25. They will all be becoming 0.1, 0.1, so it was close to a tenth. The ones on the right here for x squared, if I write that as a limit, we know that it's going to 3 squared, which is the 9. The limit is going towards 3. All these answers are getting close to 6. And the same thing for the bottom here. The limit here is going to 5 because of what I gave you for the average rate of change, 4.5 to 5, 4.9 to 5. These answers are getting close to 10 there. So we talked about this also in the last unit. So what is happening as we move from graph 1 to graph 4 here? So taking a look there, what's happening to that line there is getting closer and closer to the function there. As we zoom in even more, as the x values become closer together for all those average rate of change, that becomes a straight line, and you don't even see the root x graph, it disappears. So that is a tangent line. So when we draw a tangent line to any curve, it intersects it at a point. So now, besides getting the limit for this example, which is a fourth, this is telling us that this is something called instantaneous slope. So this is an important new word, or the slope of the tangent line of this function root x at x equals 4 is a fourth. So that's barely increasing there. So we're looking at slope now for limits. So in your notes, make sure you have this instantaneous slope or slope of the tangent line. As the 2 points become closer and closer together, that secant, average rate of change that we were doing, starts to become a tangent, which is your instantaneous rate of change, which is your instantaneous slope. So we did talk about this in the last unit, but let's have it again in our notes. So we need to know what each piece of this instantaneous slope formula is. We got our function f of x. we're subtracting our f of c, which is what the limit's going to, over x minus c. And again, as those points get closer together, that average rate of change becomes that tangent line, which is the instantaneous slope formula. So again, making sure that you have this in your notes. Okay, so for this practice here, copy down these 3 examples on the left. And what I'd like you to do is label what f of x is, what f of c is, and what c is for that instantaneous slope formula. And then we're going to evaluate the limit algebraically or using patterns from the last unit, and then explain the meaning in a few words. So let's do the first one together. So for this one here, what's my f of x? So my f of x for this one is x root x plus 7. My f of c there is 3. And my c is going to be 2. So this is telling us the instantaneous slope at x equals 2 is going to be, so I'm going to plug in the 2 there, root 9, 3. Is, now if you remember the pattern, it's 1 over 2 times putting that limit in under the square root. So 1 over 2 times root 9, 1 over 2 times 3. So the instantaneous slope at x equals 2 is 1/6. You go ahead and try these other 2 examples here. On the next slide, it gives you the answer. So hopefully you got the second one right there. The slope of the tangent line at x equals 5 is negative 1/9. And these are your 3 f of x, f of c, and c. And the same thing for this bottom one. Okay, so now you're going to practice what you just did with these notes here that I got. So you're going to go back to Google Classroom and take a look at the slides called Day 1, Instantaneous Slope Card Sort. Follow the instructions on the slides. You're moving things around or inserting text boxes there. So I'd like you to do this. This should be done before the end of class because remember this is a homework-free weekend, so you want to get it done now. And then once that's done, you could work with other people on that. Just submit your own. You could come back here to the video and get the rest of the lesson today, which is about the limit definition of a derivative. Okay, welcome back everybody. Hopefully you completed that card sort. Now we're getting into what is a derivative based on limits. So this is, and this should be in your notes, this is the actual limit definition of a derivative. This is the symbol for a derivative. F prime, that little thing there, prime of x equals the limit as h is going to 0. And it's of f of x plus h minus f of x, all divided by h. So again, this is the symbol for derivative. It represents the instantaneous slope of a function at any x value I give you. So limits are real important to find instantaneous slope, as you just learned. This lovely graph over here, I'm going to explain how they're getting this from the limit. So let's move on. How do we construct this derivative? Again, this is the general definition, the instantaneous slope formula. It gives us the slope of the function at a specific value. So let's say I wanted to know what is the slope of x squared minus 16 specifically at x equals 10. This formula will help you find it. So let's take a look at the graph. So let's draw this picture in our note. So here we have our curve. We are starting with a generic x value there. That value, we're going to input that and get our output, f of x on the y-axis. So there it is. Next, we need to add another small amount to get another x value, and this value, we're going to call it x plus h. So we're adding a new value onto the original x. The difference in the x values is h there. Then I need the output for that, so I'm going to do f of x plus h. So what we're basically doing again is finding that distance that gets closer and closer and closer to get the slope. So we're going to find, average rate of change between the 2 points. So I am taking my y2, right? This is my y2, my y1. This is my x2, and this is my x1. And as you can see here, we are replacing them in the formula. Change in y's over change in x's. Can't do anything to the top, but we can cancel the x's on the bottom. Next, we will take a limit as h approaches 0, which will bring these points really close together since h was the difference in the 2 points. So a general definition for the derivative is always the limit's going to 0. Since this was some generic point x, this limit represents the slope for any input that we want. So here's our general derivative formula. All right, so let's take a look at a function. Let's take the function f of x equals x squared. And I'm going to do the general derivative formula, which again is the limit as h goes to 0. And it's f of x plus h minus f of x all over h. All right, so how am I getting f of x plus h? Well, I'm going to replace x plus h inside the x squared. So it's going to say x plus h squared. And I'm plugging it right in the equation there for the f of x plus h. I'm subtracting f of x, so this is my f of x. This was my f of x plus h, all divided by h. Now we need to simplify. So I need to multiply out x plus h squared here. So think about it, you're doing x plus h times x plus h. X times x is x squared. X times h is xh. X times h is xh, so that's why I'm getting 2 xh's. And then h times h is h squared. So let me erase this. So this thing here is evaluated here. And I'm bringing out minus x squared, all divided by the h still. So what do you notice? These two terms cancel out, and I'm left with 2xh plus h squared, all over h still. I could cancel some h's there, so I could pull out an h from the 2xh, and I could pull out an h from the h squared. I'm left with this inside. These h's are going to cancel, and now I'm left with 2x plus h. Now I could plug in my limit. This is 0. So my answer for my derivative of x squared, the derivative of, the derivative of x squared, f prime of x, is 2x. So I could find the slope of this function, x squared, at any point on this thing because now I have the general derivative. So let's say I wanted to figure out the slope of x squared, the derivative, specifically at 4. So we know our general derivative is 2x, so I'm going to plug in 4 for the x. 2 times 4 is 8. Which happens to be the same exact thing if I was to actually do the long way that we learned from the last unit, remembering that pattern there. I'm also getting an 8. Let's take a look at another one. If I have, again, finding the derivative specifically at the point 9, the slope at 9, I'm going to use 2x again, except I'm going to plug in 9 now. 2 times 9 is 18. Again, same thing that we did from the last time. This should say equals 18. I could ask also for the derivative, the slope at this specific point, 15. We know it's 2x, so 2 times 15 is 30. All right, let's try one more example. Let's do the one with the square root of x plus 11. So I'm going to use that general derivative formula. I need a f of x plus h minus f of x all over h, right? So let's do f of x plus h. So here is what f of x plus h is. I'm just replacing the x with x plus h, keeping the plus 11. Be careful here because now here is the equation. Here's my f of x plus h. This is my f of x, all divided by h. So I can't subtract these here, so I need to multiply by the conjugate. Okay, so the conjugate is all this, right? Same thing, except we're changing the minus to a plus. So I have it over here. I wrote it out. Real quickly, let's talk about this. If I'm taking this and I multiply it by this, I'm going to be getting what we have right here, x plus 11 plus h. If I multiply the outer and the inner terms, those are going to cancel. And then if I multiply the last terms, root x plus 11 times root x plus 11, I'm getting minus, which is over here, x plus 11 in parentheses. So let's take a look at this. What's going to happen here? I need to distribute this negative inside, so it's going to become negative x and minus 11. So the x's are going to cancel. The 11's are going to cancel. And all I'm left with on the top of the numerator is h. The bottom, remember, top and bottom, you got to multiply by the conjugate. So the h is coming along, multiplying it by that conjugate I had, which is coming over here. What happens now? The h is going to cancel. So I'm left with 1 over that bottom piece, 1 over this whole bottom piece. Now I'm going to plug in 0 for h, which is shown. So that's basically 1 over root x plus 11 plus root x plus 11. So how many are these? 2 of them. So my derivative, my general derivative for square root of x plus 11 is 1 over 2 times x plus 11. So this is exactly the same thing as that pattern for these. So do you remember the pattern? It was 1 over 2 times the limit plugged in. So for this first example, it would be this, which is 1 over 2 times root 9, which is 1 over 2 times 3, which is 1/6. So if I have my general derivative equation already, which is here that I just circled that we figured out, all you're doing to figure out the derivative specifically at the point -2, I'm just plugging it in, getting 1/6. Same thing if I ask you to find the derivative specifically at the point 5, I'm going to use that same answer, 1 over 2 times that derivative formula, x plus 11, plug in the 5, and I'm going to get 1/8. So this simplifies stuff for us for when we're finding out derivatives, slopes. So let's just kind of sum up what we did today. So derivatives are constructed by finding that average rate of change between the 2 points. As they get closer and closer together, we're taking that limit of those 2 points. The limit definition of the derivative gives us a function that tells us the slope of the tangent line at any x value. So at any x value, I could get the slope. And we're going to keep moving on in this unit. Next class, when I come back, you'll be seeing patterns that are going to emerge as we find derivatives, and it's going to be so much quicker besides looking at their limits. Okay, that's all I have for today, everybody. So please remember to submit that card sort thing by the end of class.